Assalamu alaikum everyone. I'm Mohsen Amin, ID 16. This was a task given to us by my professor Dr. Mahmudul Hassan Raju sir in our 8th semester machine learning course. He told us to present about a topic he taught in class, upload it on YouTube, and then send him the link. This is both a humiliation ritual and a great learning experience, and I'm loving it. Now, beginning with decision trees. What is decision tree? Decision trees are trees like flowchart. They produce binary trees, mimics how humans take decisions. Like if I teach you intuitively, like if it's a sunny day and it's hot, you've been out to the sun, and I present to you a cold drink. Will you drink it? Yes, you will. It's cold. It's hot. You're thirsty. You've been out. Of course, you need that drink. Now let's say it's a wintry day. You've been out and you are prone to cold allergy, and I present to you a cold coffee. Now, will you drink it? No. A hot coffee, maybe, but not the cold one. No. We take decisions like that, whether we talk it out aloud or not. We do that, and decision trees mimics just that. A decision tree is made up of root node, internal nodes, and leaf nodes. The root node is the node from where the decision trees begin. The internal nodes are nodes where decision is taken depending upon a feature, and leaf nodes are node where a decision is formed and from where no new branches emerge. Classification and regression trees. Umbrella term CART refers to algorithm classification and regression trees. There are many other algorithms like CART where decision tree is used. I mean ID3, C4.5 CART, CHAID. I don't know if it's called shade. But we'll learn about ID3 and CART today because that's all I know, honestly speaking. In CART, classification trees and regression trees are used depending if the data is categorical or continuous. If it's categorical data, then it will be whether or not a tissue sample is malignant, or whether or not you will drink cold coffee. If it's a continuous data, then the data will work on house house price predicting house prices or utility prices. Entropy and information gain is used on ID3 algorithm where we calculate entropy, mother entropy. We calculate information gain of each individual by subtracting the weighted entropy of each individual features from the mother entropy that I said. I'm not sure if it's called mother entropy, but I call it mother entropy for the sake of remembering it. Helps easier to remember and understand it. The features with the most information gain are selected as the root node or the node of a branch. This goes on and on and on until the information gain is 1. That means the measuring purity, the measuring node is pure. Gene impurity is used on CART, classification and regression trees. It is when we subtract 1 by the squared summation of the probability of a decision happening or not happening. Not happening. This is the Gini. This is not Gini. This is the Gini impurity. I forgot to add another formula. This is the formula of Gini impurity, but the formula of Gini is we use summation of weighted weighted Gini impurities of two branches, and then we get Gini. The features with the lowest Gini are chosen as the root node of a branch. Yeah, you heard me right. This goes on and on and on until we get zero Gini. That means we stumbled upon leaf node where the Gini is pure. This is how CART uses gene impurity to draw a binary decision tree. Decision tree itself is if X parameter meets Y, then choose Z or W. This is decision trees as a in their most basic form. It's an if-else term that is used to make interpretable human-like decision. I mean, it mimics human-like decision. I'm not saying it is human-like decision, but it mimics it, and it is interpretable. Which brings us to its evaluations and limitation. The advantages of decision tree is that it's interpretable. It works both on categorical and continuous data. It mimics human reasoning and requires little data processing. The disadvantages are it can overfit data. I mean, it can memorize noises from the data sets, and a single alteration of in the data can change the whole structure of the decision tree. And did I forget to mention they're biased. I mean, the features the features eminent or not, with the lowest Gini will be preferred from over all the other features that are good at predicting. But due to its Gini being low, it will get more favor from the card. That is where our random forest comes. Random forest is the amalgamation of the many decision trees that are formed using the random features. Random forest is, I mean, you see how we form decision trees, right? Like using entropy, information gain, and Gini impurity. We take n random subsets of feature from the dataset. We build decision trees. We build lots of decision trees like that. We let all the decision tree make a decision, and then we ensemble the results. What happens here is it blocks out, they cancel out all the noises from the wrong decision trees, and the right predictions or decisions emerge victorious. It's like if I teach you intuitively that if you took opinions about something, if you took opinions about something from a single person, that is decision tree, the person being the decision tree. If you took opinions about something from many person, that is a random forest where each individual is a decision tree. Now, a question to you: which opinion will you rather take? The one given by a single person or the one given by many person? Of course, everyone will not give the same opinion, but you will ensemble those opinions and pick the right one, the one that works for you, right? Such is the case with random forest. Aggregating or bagging, it is called, is how a random forest takes a decision. What happens here is if there are n samples, certain samples are omitted and redundantly replaced by other samples in that row, and some datasets are left out of the tree subset so that we can safely measure its accuracy. It is done through a technique called bootstrapping. You can see in the example I've given the original dataset A, B, C, D, E. We then create three samples out of it. In the first one, we omitted B, then we replaced it with A. In the second one, we omitted A and D, replaced with them respectively with B and E. In the third one, we omitted C and replaced them with D. Subspace sampling is where the real magic begins. It forces the trees to think differently. If one feature in a dataset is highly dominant, the trees will for sure pick that feature. So what will happen here is that every single decision tree will look identical. What happens in feature subspace sampling is that in each node, majority of the features are locked out. Scanned few randomly selected features are used, and card or ID tree, I mean information gain or gene impurity is used to make those form those trees. What happens here is that The less dominant features are gets to express themselves, and the decision trees don't look identical. They're decorrelated. They don't look identical. They for this main thing, for feature subspace sampling, each trees in a random forest, each decision tree in a random forest looks different. Yeah, yeah, it's on. After all that, we aggregate the outputs. If it was on a categorical data, I mean yes or no, malignant or benign, then the majority of the decisions wins. If it was done on continuous data like house prices, CGP or anything, then the average wins. This is what differentiates random forest from decision trees. Random forest is democracy and decision trees are is an autocracy. I love autocracy. I have shown you, demonstrated you the difference of accuracy and interpretability of random forest and decision trees. As you can see, a single tree is leagues behind random forest when it comes to accuracy, but leagues ahead when it comes to interpretability. I mean, it is one tree, one damn tree. Of course, it is interpretable. And a random forest is the aggregation of all the outcomes of all the decision tree meant. Of course, it will be less interpretable, but the trade-off here is what it lacks for interpretability, it makes up for its accuracy. I'm talking about random forest. I've done earlier, I've worked with uh, Wisconsin breast cancer dataset. In here, I've ran both decision tree and random forest. This is the result. This is the top 10 feature importance in decision tree and in random forest. Could you see the difference? Yeah, look, perimeter worst was the dominant feature in decision tree, but it is nowhere to be seen. Yeah, it's number 5. It's in number 5, perimeter worst when it comes to random forest. Why? Because random forest is much more accurate. It lets uh, the other features speak for themselves. You can see this here is worked on a, I mean, this here is a real data, worked on real data. I mean, decision tree and random forest worked on a real data. Yeah, random forest stomps. Thank you everyone for tolerating me. I know this is painful to watch because not was because yeah, this is my first time presenting anything before a camera, or was it? I don't know. If you have any questions, now is the time to ask. No, no questions. Yeah, I love this.